Hello and welcome back to today's lecture. We're going to discuss our exam 1 topics in our next session or in the following discussion. And we'll start with an overview of some of our earlier material and research design, and primarily discuss vocabulary from research design you need to know, a little bit about histograms, the average and standard deviation chapters, and some of the normal approximation for data. And if you are itching for discussion of measurement error, then I'll refer you back to our previous lecture on the topic. You can run, but you can't hide from our first statistics exam. It's coming for you, but it's only coming really slowly. And like this adorable little dog, you still have time to avoid the big slimy snail of the statistics exam, which in and of itself is really not that bad. It just looks scary. It's really can be pretty cute. Or not cute, but it might look worse than it actually is. A snail is not actually dangerous. Neither is our exam. Just get ready, pay attention to the fact that it's coming, and do your best. Oops. Imagine there's a cute picture here, and we'll discuss research design. I want to start with an overview of just some summary topics we discussed across a couple of these early chapters and put them together here for you real discreetly. So first so variables are lists of numbers that are all related, all measured in the same sampling or population. And we can classify variables as either discrete or continuous. A discrete variable is one that is fully categorical. There's like male and female, race, religion. There is no in between on these. You're one thing or the other. And I'm putting a little asterisk by gender. I'm not trying to be insensitive to the transgender movement. I'm using, standard survey measurements to find these things as discrete. If we wanted to measure gender in a way that was continuous, we would have to quantify it and refine a measurement. We wouldn't be using male and female as our categories. We would be using a more refined scale. So discrete variables have no order among them, but continuous variables do. A continuous variable would be ordinal or interval or ratio, and the continuous variable has a clear order among the points in your data set. And levels of measurement are an important topic because we're going to use levels of measurement as a primary point of interest in lots of our future topics. So you need to be able to, if presented with a variable, decide what level of measurement is that variable. And then each of these levels of measurement has certain measures of central tendency, measures of variability, and then, as we'll get into in the next portion of our class, particular statistical tests that are valid for that level of measurement. And so you'll need to keep this in mind, and that's why it's so important to be able to accurately classify variables based on their levels of measurement. And not just that, but remember what goes with what level of measurement. So when we have a nominal level of measurement, we've got a variable that's fully discrete and categorical. It's, again, no hierarchy here. An ordinal variable differs from a nominal variable in that you still have we've now got a clear order among our categories, but the distance from one category to the next might not always be the same. So they're ranked, but the distance between points in your measurement is not the same. It could be variable. Whereas an interval or interval / ratio, however you see it identified, is defined by the fact that this is a variable with a clear scale and the difference between each point is always the same. It has either a definite 0 point or a imposed 0 point. And when we have an interval level of measurement, we have a lot of freedom for which measures of central tendency and which measures of variability we can use. And as we discuss these topics later, we're going to keep revisiting these levels of measurement and thinking about what measure of variability and what measure of central tendency is appropriate for each level of measurement. Finally, we have predictor and outcome variables, also known as an independent variable and the dependent variable. The independent variable is the predictor. This is the variable that you use to group your participants. And we expect that the independent variable is going to predict the dependent variable. The dependent variable is your outcome measure. The dependent variable is the one you are measuring. It's dependent on the independent variable. We also discussed experimental design. An experiment features a treatment group and a control group. A treatment group, broadly speaking, is the one that gets some kind of intervention. You are changing something they're exposed to, and the control group is getting something, treatment as normal or placebo. And we use this two-group comparison as our independent variable. So whether a participant is in the treatment group or the control group, that's the independent variable, treatment or control, and then it's predicting whatever outcome variable you're measuring. And we have some examples to discuss in a minute. But some important considerations to remember when designing an experiment are that in order to have a valid experiment and to use the powerful tools statistically that are available to us when we do an experiment, you must have random sampling of participants and random assignment of participants to groups. This is crucial. If there's any kind of bias in the way that participants are assigned to groups, it'll bias the outcome. And finally, only an experiment offers us the opportunity to make causal conclusions. So experimental research, we can control the exposure or the treatment, and because we can control that and have random sampling, random assignment to groups, and also blinding, or a situation where the participant doesn't know what group they're in, or double blinding when the experimenter doesn't know either. As long as we have these qualities in our experiment, we can draw causal conclusions validly. This is in contrast to observational research, where we can't draw causal conclusions. we can only look at whether there's some kind of relationship or association between our two variables, but we don't know what direction the association goes in. Let's look at just a couple types of observational research that we've looked at in class. We talked about surveys. Surveys are observational because in a survey, you're asking a participant after the fact to report on something that happened before. So they are observing their previous life or behavior or exposures and reporting to you in a survey. And so you're not controlling prospectively what's happening. You're just looking at something that's already happened and drawing conclusions from those data, and you can't control for other things that may have co-occurred. A content analysis is also observational research. We didn't discuss this much, but this is quite simply just when you have content and, for example, media content, and then use analyses to observe the trends in the content. And a nice example is a study I have found about the language used in the Disney princess movies, which interestingly found that in the first wave of Disney princess movies like Snow White and Cinderella, the older Disney princess movies, and it compared the language used by the female characters and the language used towards the female characters. And it compared that language to the second wave of Disney princess movies, the movies from Little Mermaid on. So Little Mermaid, Mulan, Beauty and the Beast, through Frozen. And I'm making the assumption that you have a passing awareness of these movies. I think it's a fair assumption to make. And when they looked at the content analysis of these Disney movies, what they literally did is transcribed all of the language used, classified it according to certain categories of interest, and they found that in the later Disney princess movies, the female characters actually talked less than they did in the earlier Disney princess movies. But in the earlier Disney princess movies, the female characters were more likely to be things like there's more female villains. The language used toward them was more stereotyped, so focusing on things like beauty and relationships rather than intelligence and creativity and other qualities like that. That improved in the later Disney princess movies. But it's a pretty surprising trend, and one that doesn't hold, although this study happened before Moana came out, in case you're curious, that does not hold up for Moana, which totally blows this content analysis out of the water. But that's how you use content analysis. And the reason I'm giving you some examples about this is that we'll look at this again in the future, and content analysis is something that's pretty available to do. You can content analyze anything you want. There's tons of media out there. You can content analyze papers, talks, anything you like. And it doesn't always have to involve transcription, but it usually does. Finally, we have a secondary analysis. And we did secondary analysis in our class already when we in lab looked at the GSS data set and used the GSS Data Explorer to look at trends across different variables. That's secondary analysis because those data were collected ahead of time by someone else, and then they made it available to us. And we did analyses separate from the original hypotheses. They were secondary. Wait, I think I'm going to this. A couple of final considerations about observational research. That's not correct. The observational research does not include, it might include random sampling of participants. Ideally, it should include random sampling of participants, but there's no random assignment to groups because you haven't grouped participants. They're just in reporting on their behavior, or they're just reporting, and so they're not in groups, but they are ideally randomly sampled. We can only draw observational conclusions about associations, not causal conclusions from observational research, and that's a really important point to remember. Finally, we have some relevant measurements we discussed early on, and that we used in some of our later discussions: proportions, percentages, a ratio, rate, and percentiles. And we'll have a chance to revisit these as we go through our items, but you should feel comfortable with these terms. Then we discussed histograms and organizing data, and discussed some basic techniques used to organize and display data, the primary one being the histogram. And we also made trend graphs of the GSS data. When we have nominal data, the pie chart is a great visualization for it, because nominal data can't be represented in a histogram, since a histogram depends on there being some ranking among your data, i.e. a histogram depends on a continuous measurement or continuous scale. We can use the proportions, percentages, and rates to compare our groups or time periods. And these graphic representations are pretty useful. You should feel comfortable reading a histogram so you can understand how the data is presented in the histogram, and specifically some of the general ideas about the intervals and their midpoints and class limits. I will not have you make a histogram for the exam, so don't worry about that. But we'll make more histograms in the future. You definitely should be able to read them. Then we've got into measures of central tendency next. And we discussed the mode, the median, and the mean. And at this point, let's just briefly think about for each level of measurement, which measure of central tendency, or which measures of central tendency are valid for that level of measurement. So let's say we have some nominal data. Let's say we have race as our nominal variable. Can we get a mode for race? Yes or no? And things are going to start speeding up now with the responding to questions, so try to start thinking fast. Can we get a mode for race? Mode is the most common response. Yes, we can get a mode for race. Mode is the only measure of central tendency that we can use when we have a nominal variable. So it's important in that respect that anytime you have a nominal variable, you remember you can get a mode. It's just the most frequent score, so there's no ranking involved at all in the mode. But can we get a mean for race? Can we get an average of the responses in our race variable? Absolutely not. We can't get a mean race. What would that be if we just look at white and black? What's the mean race? Gray? There is no valid scale among these variables. In order to use the mean, we must have a variable that has an interval quality. Now, the median, which is just the point at which 50% of the data is above that point and 50% is below, we can use the median with ordinal and interval data. We can use the median with interval data as well, and depending on our distribution, whether it's skewed or not, that's going to tell us whether or not the median or the mean would be the best measure of central tendency when you're looking at an interval variable. Measures of variability included the range, the deviation, the standard deviation, and then I briefly introduced the variance as a step in calculating the standard deviation. But it is important to know you'll definitely need to, you'll see that again in the future, as well as the standard deviation. The range gives us a simple measurement of the top score to the bottom score. A deviation tells us the amount that individual scores deviated from the mean. The standard deviation goes further and gives us a standardized measurement that we can compare across distributions of the variability in our sample. And as we know from our discussion today of measurement error, that the standard deviation also tells us the expected amount of chance error that we would expect in any individual measurement. And you should be able to calculate these things. And we'll practice that in just a moment. Finally, we did discuss the normal approximation for data, and there's a really nice lecture that is already available in your media gallery about the normal approximation for data, and we go over all of the pertinent topics in that lecture. For example, the characteristics of the normal curve, the properties including that it's symmetrical, it's unimodal, etc., and the various ways we can use the normal curve. And rather than go through all of this material again today, since we just did it yesterday, I'm going to keep our practice of the normal curve topics down to some problems that are be relevant on your exam. But we did a ton of problems in this lecture. So if you have many questions about that, I definitely would encourage you to review this lecture, where we really only discussed in lecture topics that will probably all be on the exam in that lecture, because there really isn't much space for other stuff. Some of it won't, but we did a lot of practice. But I do want to highlight this point, which is that you need to know the areas that are between standard deviations, the areas under the normal curve. And so we discussed this. What is the proportion of the distribution that lies above and below one standard deviation from the mean? Does anyone remember? 68%, exactly. How about at 2 standard deviations? 95%, excellent. And 3 standard deviations? 99.7%, excellent. And one final review point, how many standard deviations would we expect how many standard deviations does it usually take to encompass the whole range? Or the range usually includes how many standard deviations? 6. So remember, we discussed how 6, how if 99.7% of the distribution lies above or below 3 standard deviations from the mean, that's 6 standard deviations total, and that's 99.7%. We never can know exactly how many standard deviations does it take to get 100% of the data in a theoretical sense, because a theoretical normal approximation, a theoretical normal curve doesn't ever end. Because we don't know where the tails finally converge at the base. I'm going to move these to the end, and then we'll do some review from the other chapters first. Here we have a frequency distribution that contains the social class of 46 people who voted Republican in a recent election. And we're looking at how was social class measured. So first, how was social class measured? Nominal, ordinal, interval. Well, let's think about how to break this down. If social class is well, the first question we need to ask ourselves is there a clear order among the levels of this variable? Do these values here have a clear order? Yes. So this variable is at least, so it can't be nominal. It's not possible for it to be nominal, because a nominal if there's any clear order, then a variable can't be nominal. It's ruled out. It has to be ordinal or interval. And so our next question is there a exact distance between each of these levels? And in this case, we'd say no, there isn't. We don't know that the difference between upper and upper middle class is the same as the difference between lower and lower middle class. And so we have to say this is an ordinal variable. Given that this is an ordinal variable, what would be our most appropriate measure of central tendency? The mode, the median, or the mean? Well, we could get a mode for this, certainly. We can get a mode for any variable, and we know that the mode would be upper. It's the most common score. But we want to use the most complex measure of central tendency. So if the median is a valid measure here, then we should use the median. And because these variables have a clear order among them, we can use the median. Could we use the mean? Could we get a mean of these values? Sorry, but we can't get a mean of these values. No, because we just have a frequency count for the number of participants in each group, and we don't have a clear difference between the groups. In order to use the mean, you must have an interval or ratio measurement, because the mean, in short, the mean involves calculations that include division, and you can only use division if you have a 0 point. Mathematically, that's why it breaks down. So it doesn't make sense. We can only get an mode or a median. Here are valid measures of central tendency. And if we were to say, well, what would be the most appropriate or the best measure of central tendency here? It would depend on your goal, but generally the best measure is the most complex one. So it would be the median. The median is more complex than the mean, than the mode, and the mean is more complex than the median. Okay. In a study on perception of facial expressions, participants must classify emotions displayed in photographs of people, such as anger, sadness, joy, disgust, fear, or surprise. Is this an nominal, ordinal, or interval scale? This is nominal. There's no clear order among these emotions. What would that order be? If you're feeling like you're not sure if there's a clear order or not, ask yourself, if there is an order, what is it? And the answer should be obvious. Now we have a similar question. The factors that determine how many children couples decide to have, and the variable in question is number of children. Is that discrete or continuous? It's continuous. And let's take this one step further. Is this variable ordinal or interval? Because remember, discrete would be just nominal, but continuous could be ordinal or interval. Yep, this is an interval variable. We know it's interval because the variable goes up in clear units. You have one child, two children, and the difference is always the same. One more like that. Now we're looking at how concept formation ability changes with age. Age is discrete or continuous. Let's assume we're talking about age measured in years. If it's age measured in years, then it's continuous. We could measure age as young or old. If I said age was measured as young or old, well, that would still be continuous, right? Because there's still a clear order. Young goes before old. But age in years would be, if we look again at, is this ordinal or interval? Age in years would be an interval measurement, whereas age as young and old would be ordinal. Oh, it's a duplicate. Now we're looking at patients as high, medium, or low risk. What's the scale here? Let's start with, is it continuous or discrete? And the faster you make some guesses at these, the faster we get through questions. High, medium, and low. Does this have high, medium, and low? Is there a clear order here? Yes, of course there is a clear order. The order would go high, medium, or low. If I mixed these up and instead they were listed high, low, or medium, we would all find that not to be incorrect. We would, I wouldn't have to even explain it to you, but you would already know, oh, those are not listed in the right order. They're supposed to go either low, medium, high, or high, medium, low. There's an order inherent here. So since, yes, there's a clear order, it has to be ordinal or interval. Is there the difference between high and low the same as the difference between low and medium? Well, we don't know for sure here. So we're going to say it's ordinal. Now we've got a set of data, and we're going to find the mode, median, and the mean. The easiest way to start this out is to put the data in order, because you need to have them in order to get the median. So you see, I've done just that, and I crossed them off as I went because I don't want to get scores in here twice. So what is the mode here? 4. We only have one score that shows up more than once, and it's 4. To get the median, we need to find the middle point in these data. And so first we need to say how many scores are here. There's 7 scores. So our data point, our median, is going to be the score in the exact middle. 1, 2, 3. This is score number 4 here. 5, 6, 7, right? So 7 here, the raw score 7, has half of the distribution above it and half of the distribution below. So the median is 7. And I'm most concerned that you can calculate the mean, or just want to make sure we're clear on the definition and more or less finding the median. But the mean is is pretty important. Let's think about the formula for the mean. We're going to get the sum of our scores, the sum of x, over n. And so if we sum all these scores, looks like Stephanie already got the mean for us. Thank you. It's 8. Assuming these data are normally distributed, do we have any reason to think that there's a skew in this distribution? Or, I mean, not assuming they're normally distributed, but if we were saying, if I asked you, do you think these are probably normally distributed? Yes or no? Actually, probably not, because we can see that the variable, if our mode is quite different than our mean, and our median is also different from the mean, and they're the trend is that they go in the same direction. So the distribution itself is going to look more or less like this, because the mean is always pulled in the direction of the skew. So the fact that the mean is higher than the mode and the median tells me that this distribution has a positive skew. Right? This would be our mode, our median is over here, and the mean is way over here. Also in this problem, calculate the deviation of each score from the mean, and I've already done that for us. How did I do that? Well, I did it in Excel, but I'm going to show you the formula here. So to get the deviation from the mean, we just took x minus x bar. So each raw score minus the mean. You can see the mean down here. And here we have our deviations. If we sum all of these deviations from the mean, true or false, the deviations from the mean will always sum to 0. Is that a true statement or false? Actually, this one is true, because deviations from the mean always sum to 0. It's just another mathematical fact that we don't have too much time to unpack, but that you should be aware of because it factors into the way we consider error later. I really appreciate all your guesses. Remember, at this point, the best thing is to just keep trying, just keep making the effort. We don't need to, you want to identify any misconceptions you have now. So don't be afraid to guess. When I took statistics, when I was in your place taking a very similar statistics class at U of M Flint in a spring semester, I asked questions like crazy. So if you're concerned that I'm going to judge you for asking too many questions, absolutely not. I am someone who asks maybe too many questions, but who asks a lot of questions, and it paid great dividends for me, and it will for you too. And I certainly won't judge you because I'm a question asker myself. Our next item here, I think I'm going to, oh, we don't need to skip it because I actually, oh, no. Already did it, but the slide got moved. So let me make sure. We're not going to create the grouped frequency distribution now. You don't have to do it for the exam. I pulled this from another review to help us think about the upper and lower limits for class intervals. So I've already made our distribution here. I took these data and grouped them into these intervals. And the spacing didn't quite copy over right. But let's just look briefly at how we establish the upper and lower limit for each interval. Note that the intervals are non-overlapping with real numbers in our data set, and that's the key take-home point here. Definitely something to remember, which is that the upper and lower limit of any interval should be a number, value that is non-overlapping with the real values in your data set. So we can see in this variable, these are all whole numbers. There's not any decimals here. And so my upper and lower limits, for example, just looking at this highest interval, are a half step below this lower limit, or a half step below the lowest real score in this interval, and a half step above the highest real score. And what's the midpoint of this interval? $27.5, exactly. The midpoint is still, you still get the midpoint by getting an average of the upper limit and the lower limit. Now we have some normal distribution problems to practice. The intelligence tests are very popular in examples like these. And now we have a reference population on this Wechsler intelligence scale for children. And it's normally distributed with a mean of 100 and a standard deviation of 15. In this problem, a school district classified children as gifted if their score was in the top 2.5% of all scores. We need to find the real score cutoff for the gifted program. So to do that, we know that we're looking for a proportion of the distribution that's 2.5% of the area here. So we can jump right into looking at our Z table. And we're looking for the area that's beyond z and is equivalent, it is equal to 2.5%, we need to get the z-score for this point. And then we can convert that z-score back into a real score. So looking at our z-table, I can see in column C that a z-score of 1.96 is exactly 2.5%. So this is 1.96 right here for our z-score. And then to convert from z back into a standard score, we would just go, or from the standard score back into a raw score, we just use x is equal to the z-score times the standard deviation plus the mean. And so that's 1.96 times 15 plus 100. And we've already done the math here and know that it's 129.4. So the cutoff whisk score is 130. Incidentally, 130 also is another number of interest. Just to highlight this real quick, we know that this is if this this is 2.5% of the population, then what percentage of the population is the rest of this? As in below 130. $97.5. Exactly. So that makes 130, or specifically 129.4. That's the score that represents the 97, actually it's the 97.5 percentile. And there's just often students get confused when doing percentiles, so it's important to remember it's all the scores below a point. We usually do speak of percentiles as whole numbers, the 97th percentile, the 98th percentile, but for the purposes of just moving through things quickly, and it's always better to be precise than to say, well, Rachel said that, we usually do it this way. Well, it's always still, if what the data you have says this is 97.5, then stick with what you've got. You're confused about how I got the percentile? Is that correct? Sigma came from the problem right here. And we discussed in last night's lecture the how we have these couple of symbols that actually this one is mu, it's the mean. Technically, it's the mean of a population. We will discuss the difference between a sample and a population mean later. And that is also, for our purposes right now, still the same as X bar. On your test, I'm not going to mix up these symbols, but your textbook is pretty light on use of symbology, and we do need some of these symbols just because it makes things a lot easier. So this one is mu. Oh, and sigma is the standard deviation. Okay, it's not essential to know these symbols right now, but that's where I got it. It's from this problem. And here we have in this first column batting average. We have some numbers related to a local softball team and their batting average. And these are the batting averages for 5 players. And you can see I've already worked out the math here, but let's, so you can use this for practice if you want to, practice doing any of these calculations. You can see the scores here and their percentile ranks, and you should definitely be able to get any of these numbers that are in this table. But we did just discuss it in such great length yesterday. Unless there's an objection, I'm not going to go over each of these calculations again, but we can take a quick look at what each one means. So remember, our mean deviation was x minus x bar. The mean deviation squared is the mean deviation squared was an individual x minus x bar value, which is then squared. So it's this value over here squared. To get the z-score, we used our formula. Z is equal to x minus x bar over the standard deviation. So in order to get the z-score from the raw data, I had to also find the standard deviation, which is right down here. And when I got the standard deviation, we used the mean deviation, got the mean deviation squared, summed them, did the variance, got the standard deviation. We used this formula. And you can see how each of these, we have cells here that represent each of these terms in stepwise. So you can use these data to practice finding some of these numbers. I do want to leave us some time to do review exercises, so I'll let you practice that on your own. But let's think a little bit about this next question, the probability of getting a number between a particular z-score and the mean. Let's say, for example, this first one only, we've got a z-score of 0.27. So if I want to know the probability of getting a batting average that's between the mean, which was 0.4634, and 0.526, which is represented by a z-score of 0.27, then I'll just go to the z-table, find the mean to z column, and look for the one that, oh wait, not the mean to z column. I already have the z-score. The z-score is 0.27. It's just so small. So here we have it. If we have a z-score of 0.27 and we want to know the area between the mean and this z-score, it's represented here in column B, and it's 10.64%. And we could find the probability. Oh, sorry. So we've got the percentage of the distribution that's between this z-score and the mean. If we want to get the probability of getting a number between that z-score and the mean, then we just take our percentage and divide by 100. Because a probability is always a number that is between 1 and 0. So our probability will be 0.1064. Okay? And the z-scores, you should be able to find the z-scores and use them to draw conclusions like this. But we've already practiced that. So let me see what we have left in here. At this point, I want to let's stop for a second. And I have a few more probability or a few more normal curve related problems for us. But we did do so many of them in the lecture on the subject. Would you like to do more of them now, or go over some of your special review exercises? I personally feel like in our session on the subject of the normal approximation, we did an example of each of the different types of probability or normal curve problems that you could see on the exam. So I don't think there's a strong need to do more of them unless there's a major objection in the audience. All right, let's look at some of these special review problems. I know some of you have done them, and I'm not going to go through them, each of them. We don't have time, and I know you may not have had time to do them yet, and it's really important for these that you do take the time to try them on your own. And if you have questions about the answers, you can't figure it out on your own, you're absolutely invited to get in touch with me, and I'll walk you through any particular problem, and I can, walk you through any problem pretty quickly. So if you've spent several minutes on a problem, that means, and you still can't figure it out, that means it's time to just reach out to me. I'll be very nice when you call and ask me for help. Some of you have already. Was I nice to you? Did I answer your questions? Was the experience of calling me rewarding? Can I get a testimonial? Yes. Yes. Thank you, Tori. Yes, it's very rewarding. Thank you. I'm very pleasant. I will be nice to you. So I promise, yes, when you call, you'll get an answer to your question. I'll be nice and happy to help you. Okay. So, especially on Saturday, feel free to get in touch. If you're studying and you need some help, just reach out to me. I'll be available for most of the day. Of course, I'm doing some things on Mother's Day, but I'll still be available on Sunday, Monday, Tuesday. I'm always available. So just reach out. And it is fine actually to text me anytime. Just only it's the calling that I like to keep between 11 to 11. There's no guarantee if you text me at 2 a.m. No guarantee I'm going to see that right away. But, as soon as I see your strangely timed text, I'll get back to you. Or if it's like 6 a.m., I'll text you back. I'm not going to call you at 6 a.m. But just to clarify, you can text anytime you like. And if you're thinking, oh, it's 9 a.m., is Rachel available to help me on the phone? Just text me and say, hey, can you help me right now? If I can, I'll help you. If I'm not available, you haven't disturbed me because I'm not available. So don't worry, I'll be nice, always very friendly to students. So let's look at our special review exercises. Oh, whoops. I'm on the wrong spot here. Oh, and here's my cute little plug for, again, calling me. Why am I encouraging you to call me so much? Because I have no life? Well, I mean, arguably, I do spend a lot of my life teaching this class, but because you really need it, it really helps when you're confused about stats. You need that expert advice. I'm your expert. I'm your stats coach, and I can help coach you through this. So don't be afraid to reach out if you get stuck when you're studying. I'll save you. And you'll probably be more comfortable than that baby squirrel. I did not have time to copy over our special review exercises, but I'm going to assume that you have your books right there. So let's go ahead and look at some of these problems. And let's start out with number 1 real quick. In a course, if the histogram for scores on the final looked like this sketch on page 105, true or false? This is because this isn't like the normal curve. There must have been something wrong with the test. That's right, it's false. A test could have any kind of distribution. It just depends on what the responses on the test look like. Variables aren't predetermined to be normally distributed. They just are sometimes or frequently. Let's look at 2. I think that one is, you should definitely know how to do that one. The standard deviation of a list is 0. Of your 4 options, what do you think this means? Feel free to just respond with the 1, 2, 3, or 4 in your votes. Well, I can see your argument. It's 2 here. All the numbers on the list are the same. And when we look at these choices, it's good to think about when you look at the choices for any of your statistics exams, it's important to remember a couple of things. For one, ask yourself, is this even a choice make any sense at all? So for number 1 here, there are no numbers on the list. That probably doesn't make sense. I mean, it actually doesn't make sense at all. If the standard deviation is 0, you still have to have numbers to get a standard deviation. So that's not even possible. But another tip for thinking about not just this multiple choice, but any multiple choice, a word to the wise for how I construct questions, which is that just because, especially if a question involves you calculating an answer, just because you calculated an answer that is one of the options available, that does not automatically make your answer the correct answer. Because when I make up multiple choice options, I'm a good test maker. I'm a statistician and I have advanced training in test construction. So I know that if I really want to be able to tell if you actually know the answer or if you're just used, got it by chance or did a close calculation or something, I'll use, what I'm getting at is I will look at, well, what are some common mistakes that students make when they're calculating, doing this type of calculation, and I'll come up with answers that make those mistakes. Some people say it's tricky. It's really just good test construction, but I'm making you aware of that proactively so that you can, test smart. I'm not trying to trick you, but I am trying to get an accurate assessment of whether or not you know how to do these items and these questions. And that little tip will become increasingly helpful as we move into more and more as we go on in the class. So just something to keep in mind. Let's look at B here. The root mean square size of a list is 0. What does that mean? 1, 2, 3, or 4? Oh, did we talk about A? Sorry about the A. Yes, so A is 2. If the standard deviation of a list is 0, that means all the numbers are the same. Yep. If we had a mean deviation of 0, that would just be something that would be expected, though, because the mean deviation is always sum to 0. Because the mean deviation doesn't, or the deviation doesn't account for sign, but the standard deviation controls for sign. So if you've got a standard deviation of 0, all the scores are the same. B, let's look at the root mean square. We should know this one. If the root RMS size of a list is 0, what does that mean? 1, 2, 3, or 4? Yes, Tori, all the numbers on the list are 0. Very good. With item 3, you should be able to do it, but we're not going to convert these scores in their units and standard units. We just talked about that at length in the previous lecture. See the discussion on the normal approximation. The same topic and with the same reasoning in mind, we're going to skip 4 tonight too. We did a bunch of SAT similar problems in the discussion on the normal approximation. But let's look at number 5. In cycle 3 of the health examination survey, there were 6,672 subjects. The sex of each subject was recorded at 2 different stages of the survey. In 17 cases, there was a discrepancy. The subject was recorded as male at one interview, female at the other. How would you account for this? Is this caused by bias or chance error? Yeah, this is just a chance error. It would be bias if the bias would have to be systematic and going in the same direction. So females were consistently classified as male or something. And it would apply to everyone, the bias. So we would consider this a recording error or a chance error. Well, it's 9 o'clock now, but if you want to, we can go through a few more of these items. Are there any particular items that you had questions about? I strongly recommend doing these items to help you prepare for the test. These are good problems and they'll give you some good practice. But if there's particular ones that if you've already done them and you think they're tricky, If you're thinking, well, I would love to go over some of these, but I haven't had a chance to do them yet, and you've already told us we should try the problems before getting feedback, I agree on all those counts. And my response to your unasked question, or you might be wondering, is that we should have some extra time after the lab lecture tomorrow. I consider, I usually plan about an hour for lab lectures, but I wouldn't expect tomorrow's to take that long at all. So we can, I'll be happy to go over some more review exercises, special review exercises then, if you do some more and there are questions. And as I said, I'll also be available on, afterwards to do that, but I don't want to schedule any sessions, for everyone during the review time. I want to do that, before our review time. So, yep, we'll be available after the lab lecture tomorrow. I'm planning to have some extra time to go over more of these items with you. But I just hate to rob you of the chance to do them on your own. And it's 9 o'clock. It's so nice to stop at the time that lecture is the time actually planned for lecture. And I think that we went over the important ideas in today's lecture. Okay. So among these, sorry about that. And so the range of problems, to just circle back real quick to Molly's earlier question of what should we expect the exam? What is the exam going to be like? Well, I think you should expect it to be a mix of problems similar to lots of the ones we did today. So there's, a fair proportion of the exam is pretty simple questions where you get to just do a multiple choice or true false response on things like classifying a variable. The things that we went through in our session today. Some other problems will have you do calculations that we discussed already. And there'll be a small number of problems that would be what I would call the more difficult problems. And how many questions? I'm still working on it, but about 50, give or take, because it just depends on how I break up some of the later questions. But the better question is, how long, how much time would you expect this to take? Less than 2 hours or less, I would say, but I'll give you a lot more time than that. So you'll have at least 4 hours available to do it. And if you go over the allotted amount of time, that's fine. You just submit your exam and I'll still grade it. You won't get any kind of points taken off or anything like that. But the Blackboard won't automatically compute your score. So it will show your score as a 0 if you submit it late, because I have to go in and manually put your score in. It's not all multiple choice, but I've maximized the an automatic scoring of items. So types of items that Blackboard can score automatically are multiple choice, fill in the blank, similar things like that. And I'm trying to fit problems into that area where there when on any of my exams, when the problems, are when there's some multiple choice problems and then some problems where you have to write out a response, I'll split the exam into 2 parts. So you can do your multiple choice or true false, the ones that will auto score, and do that part separately, get your score right away for that. And then you don't have, you're not you're only waiting on my grading of the, key items that are in the part 2 or whatever part that has to be manually graded, if that makes sense. And I break it up like that just to help you be able to access your results more quickly. Generally, students are very concerned about getting their scores as quickly as possible. Okay. Any other questions? Okay, that's great, Molly. Remember, if you come up with any more questions about the exam, we'll take some time to discuss it after the lab lecture tomorrow. So you're not out in the cold. Keep the eye of the tiger. Remember to keep feeling strong and powerful about your statistics, your growing knowledge of statistics, and good luck tackling the exam. Have as much fun as these kittens. May the odds be ever in your favor.